Okay, welcome everybody to the Learning to Program in C episode 3 stream. Let's get going. We left off on episode 2, looking at chapter 4. If you remember, we started with the compiling and debugging, learned how to use make, some gotchas in make, and then we spent some time in the GNU debugger. We got right to the section before Valgrind. So what I'd like to do today is first off open Emacs, move it over here, and then do our snapping windows so we get a full screen. And let's just open up projects. We'll go see Chapter 4, we had bogus, we had mystery, we had failed. Let's just find one. Let's just do another one. Let's just say review.c, and we'll include sdi.h. If we remember yesterday, we'll do an int main void function, and then we'll just do printf hello world, and then we'll return 0. So it should be the most basic we have, and then we'll compile using gcc minus g3. Just 1 second, my wife's calling me. Hey babe. Hey, I was just started streaming. So, are you on your way home? I'll see you when you get home. Love you. Bye. You're... Okay. My apologies for that. That's real life streaming here. Okay, so back into our mini buffer. G3, we'll do -O. We'll say that this was review. And review.c. Compilation finished. Do compile again, and then we'll delete that and then just do review. There we go. Hello world. So that worked. We also, if you remember in the beginning of the chapter, we also learned about the make files. So let's just quickly review that because I want to practice, even though I'm not doing large make files now. I did watch a few videos. There was actually a 60 seconds make overview in 60-second video, which was very, very cool. I'll add that to the description. Let me make note to add that to the description. We'll do Alt-T. And to description the make video, and then I'll set that for today, so I'll get that done after the stream is done. Okay, so I digress. So let's just do a make file, and then if you remember, we're going to set the flag to GCC, and we'll set C flags to G3, and then wall. Then there's others that I want to do eventually, but I haven't got them yet. And then well, all is just review here, review, and then the review target's going to be review.o, and then the command for that to create that is just cc, and then we're going to bring in the C flags as well, and then -O, and then at, and then don't quite remember what that does. And then we'll just say echo, I just built review. Okay. And then we'll do that review.o as a target, just creates, include review.c. And then we're gonna have a test, and we'll do review, and then the command will just be running review, and then we'll echo test ran successfully. And then I want to do a clean as well. We'll do a clean target, and then that's just rm, and then review, and then any, let's just do review dot star. No, review and so the remove, I don't remove the review a target, try to rebuild everything. The remove, let's let you make clean, get rid of anything you can rebuild. Oh, okay. Yeah. So it would just be, so the things that I would be able to rebuild, like the O file, the header files. Okay, so that's pretty much it. Now if we do compile and we run make, okay, save file, yes. Command not found. Review.c, command not found. Review.o. Oh, that's the command. Okay. Try that again then. Oh, there we go. I just built review. So, okay, now if I do the test, make test. Test ran successfully. Cool. And then I can do compile. Well, let's first do Jared. Control XD. Okay, I forgot that's Control XD. So we see we have where's review? Row. Control XD. We're still not seeing a review. Review.c, yeah. Okay, so do compile. Make clean. Okay. Oh. No changes to be saved. Compile. Make test again. Okay. There we go. Review. I just review. Hello. Okay. So. My apologies. So that means that we're going to go back and do compiling checks later on in life. I got to get back to Valgrind. There we go. And then real quick before that, let's do a GDB too. So let's say GDB, and we'll do review. Okay, and we'll do break. Okay, let's do list. Let's break on 4, break 4, run, print. Cool. Continue. There we go. Then we can quit it. We'll go back to review. All right. Let's go start reading then. All right. Valgrind. The Valgrind program can be used to detect some, but not all common errors in C programs that use pointers and dynamic storage allocation. You can run Valgrind on your program by putting Valgrind at the start of the command line. Valgrind, and then the program, and then the test input. This will run your program and produce a report of any allocations and deallocations it did. It will also warn you about common errors like using uninitialized memory, dereferencing pointers to strange places, writing off the end of blocks allocated using malloc, or failing to free blocks. You can suppress all of the output except errors using the -Q option like this. Valgrind -Q / my program arg test. You can also turn on more test, example Valgrind tool, memcheck, leak check. See Valgrind help for more information about the many options, or look at the documentation at http://valgrind.org for detailed information about what the output means. Some common Valgrind messages, see the examples. If you want to run Valgrind on your own machine, you may be able to find a version that works at. Unfortunately, this is only likely to work if you're running a Unix. Like this does not include Linux, either on its own or inside Windows Subsystem OS, but it does not include stock Windows. If you want to run Valgrind on your own machine, so is Valgrind a web-based something? Tech memory, Valgrind distribution includes 7 production qualities tools. Oh, interesting. Okay. So let's put that in the notes that we want to clear up any misunderstandings of Valgrind. Okay. Back to Valgrind. Okay. Compilation flags. You can run Valgrind in any program. Try Valgrind ls. It does not require special compilation. However, the output of Valgrind will be more informative if you compile your program with debugging information turned on using the G or G3 flags. This is also useful if you plan to watch your program running using GDP. Automated testing. Unless otherwise specified, automated testing of your program will be done using the script in CS223 bin VG. This runs CS223 bin Valgrind with the tool memcheck, leak check yes, and Q options. Throws away your program's output and replaces Valgrinds. If you have a program named prog running, should produce no output. Okay, so the reason that this is showing up, I think, is because this book was originally written for a CS course, computer science course, and then was released under the Creative Commons license. Which I forgot to say in the beginning, I'm streaming this video under a Creative Commons 4 share alike license. So it was created for this class and then released, and I think the Codeahoy just forgot to remove this particular from there. So don't worry about that. Like, obviously, we're not going to have that folder. Examples of some common Valgrind errors. Here are some examples of Valgrind output. In each case, the example program is compiled with -G3 so that Valgrind can report line numbers from the source code. You may also find it helpful to play with this demo program. Uninitialized values. Consider this unfortunate program which attempts to compare two strings, one of which we forget to ensure was null terminated. Include standard input output, int main argc char a0 equals a if string comp a puts. Okay, so I don't know what that particular function even does. Let's see if we can find that. So we'll go Q, let's do info stio, and then let's search for okay. So that's not even a function. Let's so where's that coming from then? Apropos. Compare two strings. How info string compare. Include string H. So I don't think that that's included as. So I think if we run this, if we program this as a, just have it here, we're gonna get a failure because that string's not included. So let's just do another video. Let's do valgrind.c. We'll do. Let's do include stio.h. Unless that includes headers with it, but I don't think it does. Let's do char a 2 a 0 equals a, I guess. If see, that's where I think I'm gonna have a problem. Not string comp a then puts a is a. Okay, and then return 0. Okay, so let's do that. Compile this. Run it without compile. Yeah. That's what I thought. We don't have that in there. So include string.h. I wonder if they should know. It's kind of hard. Like, do I tell them, or do I just keep on using the book and continue learning? Because I caught that, but some of you younger programmers out there might not catch that. That's see, now it compiles. And then we can just run it. Oh, compile. Let's see, Valgrind. A is A. Okay. So let's do it with Valgrind then. Compile. Valgrind minus Q Valgrind. Command not found. Do I need to install Valgrind? I think it's Dabby Dank. Wrong password. There we go. Yep. I didn't have Valgrind installed. So I'm installing Valgrind. Now that it's installed, we'll run that compile command again. There we go. So conditional jump or move depends on uninitialized values at, that memory address is different. String comp in user mem. Here we get a lot of errors, but they are all complaining about the same call to string comp. Since it's unlikely that string comp itself is buggy, we have to assume I don't see. Yeah, string comp. Okay. And string comp. Since it's unlikely string comp itself, we have to assume that we pass some uninitialized location into it that it is looking at. The fix is to add an assignment at A1 equals \0 so that no such location exists. Oh, I see. Because we said give us a char of length 2, and we only initialize the first element of the char. So what is the second element of the char? It's uninitialized. So what happens if we debug that then? GDB Valgrind and let's say break list break 9. Okay, run print A. Oh, because char A. Play A. Print A0. 97. Okay, print. What is A1? Ah. So that's the uninitialized. I don't know what that slash what is /000 /000 byte. Character constant. Okay, so Stack Overflow is having some help. So it's saying that boom char hard each digit is 3 bits. Each digit is 4 bits. Okay, so what? In C strings determined by character values, this could be written like this: char 0. There's a special syntax usage where the backslash works as an escape sequence. Introduction is followed by various things. One such sequence is \0 that simply means a character with the value 0. Thus you can write things like this. Another sequence uses a backslash followed by a letter X and 1 or 2 hexadecimals. I'm working on finishing chapter 4 with Valgrind. There's important constant. Octo, they use backslash followed by just as octo constants is just. You construct a string containing non-printing characters. What if you want to write? This did not answer. This didn't answer it. I want to know what that. Yeah, there we go. GDP when displaying the value of a variable storing such a character. Yeah. GDP seems to always use 3 octodiscs to display character, and for a good reason. Consider the following string. Then, this is because C standard says that an escape sequence consists of a maximum of 3 octodigits. Thus, if you write, it means string literal of 2 characters, null followed by A. But if you write, it means a string literal of 1 character, ASCII code 1, start of header, control character. In fact, the standard. The shortest way to write ASCII null followed by the digit in a string literal. The record is an octo escape sequence of a character constant. An octo escape sequence may contain at most 3 octodigits. Okay, kind of understand then. Okay. Moving back on. Okay. Bytes definitely lost. Here's a program that calls malloc but not free. You know what? We're not even working with this yet. Let's see. Performance tuning. Profiling with graph. You know what? I think that we're going to revisit chapter 4 with this stuff, because this is getting into performance tuning. This is getting into things that, like, they're talking about malloc. I don't even know what malloc is yet. I haven't used it. So, because of that, let's just make a note to, oops. Revisit chapter 4 after learning more concepts. Okay. So that means we're going to go back to the index and go to chapter 5. I think that, yeah, this is optimization. This is stuff that's, I kind of wish they wouldn't have put it in this order. And then introduction to Git. Oh man. I already know how to use Git, so we're gonna skip Git. We could go back to the if there's questions. Here's the C programming language. This is the grift of it. So we're getting to chapter 6. We finally get to dive into the C language. Pardon me. The C programming language was developed at Bell Laboratories in the early 1970s as the system programming language for Unix. Based on the earlier and even more primitive languages BC, PL, and B, when originally developed, it was targeted at machines that were extremely limited by modern standards. The first Unix implementation and the B compiler that supported it ran on a DEC PDP-7 with only 8,192 18-bit words of memory. Dennis M. Ritchie, the development of the C language in Thomas J. Bergen Jr. and Richard J. History Programming Languages number 2, Acme Press 1996. So this is what they said. So it was ran on a DEC PDP-7 with 8,192 18-bit words of memory. So using as few resources as possible, both in a compiler and then the resulting code, was a priority. This priority is reflected in the features and lack of features of C. Features and lack of features. So this is kind of what I'm looking forward to. That C, a lot of things that you want to do in C, you kind of got to spin up and do yourself. So with priorities reflected in the features, and I think the priority of the features is that you do have control to all of your memory, all of your addresses. You get these kind of silly things that we were just looking at where there's 3 octal bits for escape sequences. This priority is reflected in the features and lack of features of C and is partly responsible for its success. Programs written in C place almost no demands on the system they run on and give the programmer nearly complete control over their execution. This allows programs that were previously written in assembly language, like operating system kernels and device drivers, to be implemented in C. So C is often the first language ported to any new architecture, and many higher level languages are either executed using interpreters written in C or use C as an intermediate language in the compilation process. Since its initial development, C has gone through 4 major versions. I said revisions. They say versions. The original KNRC, defined in the 1978 first edition of Kernighan and Ritchie's book, The C Programming Language. That's a hard book to find. ANSI C from 1988, which is fixed some oddities in the syntax and which is documented in the 1988 second edition of the C programming language. C99 from 1999, the ISO IEC 9899 1999 standard for C, which added some features from C++ and many new features for high performance numerical computing. Very interesting. So C later on took features from C++, which C++ was initially based on C by I'm going to forget his name. I will come back to it in a little bit. It's top of my head. The creator of C++. C11 from 2011, the ISO IEC 9899 2001 standard for C, which relaxed some of the requirements of C99 that most compilers hadn't bothered implementing and which added a few extra features. Unfortunately, C99 and C11 both exemplify the usefulness of standards committees in general and the ISO in particular, because the ISO has no power to enforce standards on compiler writers, and because they would charge you CHF 198 just to look at the C11 standard, many compiler writers have ignored much of C99 and C11. In particular, Microsoft pretty much gave up on adding any features after ANSI C. Oh, so in 1988 Microsoft gave up? And support for C99 and C11 is spotty in GCC and Clang, the 2 dominant open source C compilers. So if you want to write portable C code, it is safest to limit yourself to features in ANSI C. So that's interesting. So that means that if I'm writing something and I want to be able to share it with other computers or other users, the portability of it, well, they're going to have to build it anyway, because even though C is portable, you still have to compile. Means that you should use ANSI C, which is the C from 1988. But I'm mostly doing this for self-improvement, and I'm probably going to write a couple tools that I want to use on my computer. So I'm going to go ahead and probably use the latest standards. And I'm assuming that this statement might be a little bit out of date. You know what? Let's ask ChatGPT. We'll just ask ChatGPT. Can you tell me if this statement is correct and up to date? Below. Okay, so let's copy that. So we want to say this comment here, I have a question about. I don't know, because that means that they would recommend you using a standard from 1988. Yeah, so it's the many common code bases. So I would say that was probably a bit of an out of date statement. So we're gonna go with using at least C11, and I think there's even a C23 standard I've watched a few days ago that's in the process of being approved. Okay, so for this class, again, this is a book, um, so not a class. You know what though? What was the class called? CS223. I wonder if we can find CS223 problem sets online. 223. Yeah, look at that. Notes on data structures and programming tricks. The textbook. What textbook are they using? Yeah. C programming language textbook. 12 homework assignments. So let's see if we can get the programming assignments. Hi, baby. I was talking to my wife. Notes. Samples. No. Let's see. Notes. Syllabus. Debugging tools. Oh, so this is what the program is based on. Very interesting. Okay. What I'll do is I'm going to be asking ChatGPT during the programming, during the development, to help me create some problems. So, since its initial development, C has gone through, yep, structures of a C program. A C program consists of one or more files which act a little bit like modules in more structured programming languages, each of which typically contains definitions of functions, each of which consists of statements which are either compound statements like if, while, etc., or expressions that typically perform some sort of arithmetic or call other functions. Files may also include declarations of global variables, not recommended. Not recommended in any language. I actually had been studying functional programming for a while over the last couple of years, and it's one of the big kind of tenets as functional programming is non-mutability. And one of the big things in order to do that is you don't have global variables. And functions will often contain declarations of local variables that can only be used inside that function. Here's a typical small C program that sums a range of integers. Since this is our first real program, it's a little heavy on the comments shown between the comment things. Okay, so let's look at it. So they're importing standard input output and standard lib. This is needed to get the declaration of ATOI. I don't even know what that is. Return the sum of all integers such that start is less than or equal to I and I is less than n. Int sum range, int start, int n, int I loop, int sum. A mathematician would use a formula for this, but we are computer programmers. So in the book, they're going to be using just ANSI C, aren't they? Yeah. So I might go through this a little bit, because then we do have Modern C too by Jens Guzdet. So I think that might be the next step after this book, depending on how non-pedantic this ends up being, like how much we can learn from this, considering that they are using ANSI C, which is a bit of an older standard. A mathematician would use a formula for this, but we are computer programmers. Sum 0. The three parts of the header for this loop mean set I to start. Yeah, we know that. For I equals start, I is less than n, I plus plus. Sum plus equals I, this adds I to the sum. This exits the function immediately, sending the value of sum back to the caller. Return sum int main, initial value in range, 1 past the last value in the range. This tests for the wrong number of arguments. The not equal to operator returns true if its arguments are not equal and false. Yeah. If argc is not equal to 3, f print f, standard error. What is f print f? Is that another typo? Oh, there is an f print f. What is f print f? Let us see. Info. F print f. F print f. Oh, file stream constant char format. I don't. That looks like those are. Okay. So that's some format string stuff. We'll learn about that later. Standard error is the file usage start and return 1. And then non-negative. A 0 is a success, and a non-0 is negative, I guess. Return 1. Convert start and end positions from strings to end. Return 0. Let's ask ChatGPT, like, why do we return 0 for success in non-negative, negative, greater than 0 for failures? Oh, because 0 means I had 0 errors. It returns 0. That's kind of cool. Oh, and then the Boolean logic, you could apply Boolean because C doesn't have an actual Boolean. Okay. Convert start and end positions from strings to int. Start because ATOI. What in the hell is ATOI? Let's see if we have an info for that. Info ATOI. Feature test macro function converts the initial portion of the string pointed to by end pointer to int. The behavior is the same as string, except it does not detect errors. Behave the same, except that they convert the initial portion of string to a return type of long. Convert start and end positions from strings to ints. Okay. Because the arguments that come in, wait, argv char. Convert to start and end positions. Call sum range and print the result. Printf, yeah. This is what the program does if we compile and run it. Contains 2 functions, sum range and main. The sum range function does the actual work, while main is the main routine of the program that gets called with the command line arguments when the program is run. Every C program must have a routine named main with these particular arguments. In addition, main may call 3 library functions: fprintf, which in this case is used to generate error messages, printf, which generates ordinary output, and atoi, which is used to translate the command line arguments into numerical values. These functions must all be declared before they can be used. In the case of sum range, putting the definition of sum range before the definition of main is enough before they can be used. Sum range. Yep. For the library routines, the include files, standard input output.h and standard lib.h, contain declarations of the functions that contain enough information about their return types and arguments that the compiler knows how to generate machine code to call them. These files are included in sumrange.c by the C preprocessor, which paste in the contents of any file specified by the include command. strips out any comments delimited by blank blank and by blank in the end. Strips out any of the comments delimited by the comment stuff in the end of the line if you're using C99, and does some other tricks that allow you to muck with the source code before the actual compiler sees it. See macros. That's chapter 18. So we're going to see macros when we get to macros. And does some tricks that, yeah, you can see that the output of the preprocessor looks like, you can see what the output of the preprocessor looks like by calling the C compiler with the -e option, as in gcc -e sumrange.c. The body of each function consists of some, I want to see what it looks like. So let's go back to Valgrind. That is compile. We'll do, oops. GCC -e Valgrind. What in the heck did I just do? Whoa. Wow. Wow. That's a lot of stuff. That's really cool. Okay. The body of each function consists of some variable declarations followed by a sequence of statements that tell the computer what to do. Unlike some languages, every variable used in a C program must be declared. A declaration specifies the type of a variable, which tells the compiler how much space to allocate for it and how to interpret some operations on its values. Statements may be compound statements like the if statement in main that executes its body only if the program is called with the wrong number of command line arguments, or the for loop in some range that executes its body as long as the test in its header remains true, or they may be simple statements that consist of a single expression followed by a semicolon. An expression is usually either a bare function call whose value is discarded, for example, the calls to fprintf and printf in main, or an arithmetic expression, which may include function calls like the calls to atoi or in main, whose value is assigned to some variable using the assignment operator equals, or sometimes variants like plus equal, which is shorthand for adding a value to an existing variable. X plus equal y is equivalent to x equals x plus y. When you compile a C program after running the preprocessor, the compiler generates assembly language code that is a human readable description of the ultimate machine code for your target CPU. Assembly language strips out all the human friendly features of your program and reduces it to simple instructions, usually involving moving things from one place to the other or performing a single arithmetic operation. For example, the C line, x equals y plus 1, add y 1 to y, store result in x, gets translated into x86 assembly as move L -24 eddy, add 1, move. These three operations copy the value of y into the CPU register %EDI, add 1 to the EDI register, and then copy the value back into x. This corresponds directly to what you would have to do to evaluate x equals y plus 1 if you could only do one very basic operation at a time and couldn't do arithmetic operations on memory locations. Fetch y, add 1, store x. Note that the CPU doesn't know about the names y and x. Instead, it computes their addresses by adding -24 and -28 respectively to the base pointer register base pointer. This is why it can be hard to debug compiled code unless you tell the compiler to keep around extra information. For an arbitrary C program, if you are using GCC, you can see what your code looks like in assembly language using the -s option. For example, GCC -s will create a file sumrange.s that looks like this. You usually don't need to look at assembly language, but it can sometimes be enlightened to see what the compiler is doing with your code. Yes, I do want to see what it's doing with my code. You had me at can be enlightened. -s. Okay. So there is now an S program? No, where's it at? I don't... Oh, G to update? That's... Oh, that's all I had to do? Okay. Valgrind.s. So this is the assembly. This is the assembly code for that Valgrind. No fucking way. Pardon my language. No flipping way. That is ridiculous. That's what assembly looks like. I mean, you can still read it, but I don't know what any of this stuff means. Very interesting. Okay. You usually don't need to look at assembly language, but it can sometimes be enlightening to see what the compiler is doing with your code. One thing that I find interesting about this particular code, which is for the x86 architecture, is that most of the instructions are move L. Yeah. The x86 instruction for copying a 32-bit quantity from one location to another. So most of what this program is doing is copying data into places expected by the library functions it is calling. Also noteworthy is that the beautiful compound statements like if and for that so eloquently express the intent of the programmer get turned into a pile of jump and conditional jump instructions. Yeah. Assembly's kind of cool then. Okay. The machine code versions of the often dangerous and confusing go-to statement. This is because CPUs are dumb. They don't know how to carry out an if branch or a loop, and all they can do instead is be told to replace the value of their program counter register with some new value instead of just incrementing it as they usually do. Assembly language is not the last stage in this process. The assembler as AS is a program that translates assembly language in some range S into machine code, which will be stored in some range O if we aren't compiling a single program all at once. Machine code is not human readable and is close to the raw stream of bytes that get stored in the computer's memory to represent a running program. The missing parts are that the addresses of each function and global variables are generally left unspecified so that they can be moved around to make room for other functions and variables coming from other files and from system libraries. The job of stitching all of these pieces together, putting everything in the right place, filling in any placeholder addresses, and generating the executable file some range that we can actually run is given to the linker, LD. The whole process looks like this. So we have the preprocessor, so the preprocessor creates some files, then the linker where does it say the compiler generates assembly language. Okay. And then the linker. So look, some range C source code preprocessor. C preprocessor. Preprocessed version of some range C. Compiler. Some range S assembly code. Assembler AS. Some range O machine code. Linker LD. So I want that. I don't know what I just did. Yeah, that's good. Oh, process. The good news is you don't actually have to run all of these steps yourself. Instead, GCC will take care of everything for you, particularly for simple programs like sum range that fit in a single file. Numeric data types. All data stored inside a computer is ultimately represented as a sequence of bits, 0 or 1 values, typically organized into words consisting of several 8-bit bytes. A typical desktop computer might have enough RAM to store 232 bytes, 4 gigabytes. A typical desktop computer might have RAM to store 2 to the 32 bytes, 4 gigabytes. However, the address space of a process might be much larger. On a 64-bit machine, the address space is 2 to the 64 bytes. There's no way to store 2 to the 64 different addresses and 2 to the 35 bytes of RAM. Instead, a memory mapper, typically built into the CPU, translates the large addresses of the parts of the address space that are actually used into smaller addresses corresponding to actual RAM locations. In some cases, regions of memory that have not been used in a while will be swapped out to disk, leaving more RAM free for other parts of the processes or other processes. Or other parts of the process or other processes. This technique is known as virtual memory and is usually invisible to the programmer. So what is the difference? Let's go to Scratch. What is the difference between is there power? Describe function. Is there power function? Power exponent math. Is there a info apropos command? Yeah. Search for command power. No. H a exponent. Okay, so I don't know how to do this in eLisp, if there's a Lisp. Let's see, eLisp power function. Yeah, math functions. Boom, boom, boom. So is that built in? So exponent. The exponent returned exponential base e of arg. Exponential. Base e of arg 2 to 2. Evaluate. Oh, XPT. Okay. XPT. So 2 to the 32. And then let's compare that to XPT 2 to the 64. I want to see what the difference is. X control E. So that's 2 to the, so 4 billion. What did they say? 4 gigabytes. Yep. Okay. And we'll never be able to have enough RAM in our system, I guess they're saying. 2 to the 64. It didn't. Did I have an overflow or something? 0. To the 64. Okay, there it is. So, all right. So let's see. That is. Oh, where'd it go? What? Why isn't it giving me the function? Evaluate. In my current experience learning C, I like it. I like it. I like it as a language. Sorry, I just saw your message. I'm still learning how to do streaming in general. Why? Hey, okay. Why doesn't it 2 to the 64? Evaluate. It's saying 0. Is it because it doesn't give you enough? No. Huh. So there is evaluate expression. And then if I do it there, 2 to the 64. Oh, it's saying 0 now. Didn't you guys see, like, if I go to the messages, there it is, right there. This is the number. This is the number. So we're looking at million, billions, trillion. I mean, that's like, okay, so that was 4. That's like 18 petabytes or something. I don't know if we're ever gonna get to our machines with that many bytes. Okay, that was a little bit of a digression. I was just using. I don't understand why it evaluated it once and then it wouldn't evaluate it again. This is kind of upsetting me a little bit. Let me just try it again. Exponent 2 to the 64. What if I do 2 to the 4th? That should be 32. Oh, no. 16. I mean 16. Okay. So 32 should give us the number that was 4.2 billion. Okay. And 64 is giving us 0. I don't know. It might be like a buffer overflow or something. Yeah, what languages have you programmed in, Pablo? Okay. So, yeah, in some cases, regions of memory that have not been used in a while will be swapped out to disk, leaving more RAM free for other parts of the process. This technique is known as virtual memory and is usually invisible to a programmer. The use of virtual memory can increase the available space beyond the size of the RAM a little bit, but if you try to run a process that is actively using significantly more space than can be stored in RAM, it will slow down dramatically because disk drives are roughly 10 million times slower. 10 million times slower than memory. Well, we have SSDs now. I don't know. So if we look back at this class that we were looking at, I don't know when this textbook was written. Let me. Let's see. Let's go here. 2023. Well, license. Oh, assignments. Can I get to assignments? No way. No. You. Oh wait, yeah. You can get assignments. Okay. Assignment 2. Okay, so we have the assignments right here. Okay, so section 8 is assignments. Okay, so let's web clip the assignments so we don't lose those depending on if this page goes away. Okay, let's do multi-select. We'll do no. Okay, what? How? So is this whole thing? Yeah, this is the whole. So. So wait a second here. Does this follow completely? So we're gonna get the C programming language, okay. This is the exact same information. Let's see what the syllabus is. Interesting. So I think I found the actual. So, okay, so if we go back to 8, where we have the assignments, does it tell you at what point that they want you to complete the assignments? Oh, sample assignments from spring. Wait a second. No way. So we have assignments from 2018, 2015. Oh my god, I love this. Okay, so I want. Let's go back to assignment spring 2015. You're to implement an encoder for a polyalphabetic substitution cipher. Okay. I'm definitely going to implement these assignments in there, but I need to know, where's the syllabus? Meeting times. A calendar. Lecture notes. Oh, yes, yes, yes. Okay. Does this tell you when the assignment is due? Okay. So let's see the calendar. Uh-huh. Oh yeah. Yeah, with all of this stuff, you're absolutely right, Pablo. And then all of this stuff is released under a Creative Commons license, so you can essentially learn everything on your own using like university level courses. I haven't gone to university. I've gone to community college. Um and then I've been a programmer for 10 years as well, but you can do all of this with just the resources that are available. Here, I'll type in the chat, the page that has. Okay, calendar. I want to see the calendar. No, I wanted to see. So this is the instructor. What was that for? The assignments were 20. That was 2022 calendar. Oh man. Okay, so let's go to calendar. We gotta go to 2022. It'd be like January because it was spring, right? Yes, there it is. Okay, so where is the... Oh, so that's just lectures, so that's not really helping. Okay. All right. That's cool. Let's go back to finish up this chapter real quick. The most basic kind of representation of data integers from some bounded range. C supports several integer data types varying in their size and thus range and whether or not they are considered to be assigned. These are described in more detail in Chapter 7. For numerical computation, integer data types can be convenient. So C also supports floating point types that consist of a fixed size mantissa, which is essentially an integer together with an exponent that is used to multiply the mantissa by 2x for some x. These allow very small or very large values to be represented with small relative error, but do not allow exact computation because of the limited precision of the mantissa. Floating point types are also described in Chapter 8. Very interesting, this word. All other data is represented by converting it to either integer or floating point numbers. But, come on, how simple is that? It's zeros and ones, and then depending on the size of your words of 8-bit bytes, you can create floating point or integer data types. All other data is represented by converting it to either integer or floating point numbers. For example, test characters in C are represented as small integer values, so that the character constant z representation, a lowercase z, is exactly the same as the integer constant 122, which is the ASCII code for z. A string like hi there is represented by a sequence of 8-bit ASCII characters with a special O character to mark the end of the string. Strings that go beyond the English characters available in the ASCII encoding are typically represented using Unicode and encoded as sequence of bytes using a particular representation called UTF-8. The color of a pixel in an image might be represented as three 8-bit integers representing the intensity of red, green, and blue in the color, while an image itself might be a long sequence of such 3-byte RGB values. At the bottom, every operation applied to these more complex data types translates into a whole lot of copies and arithmetic operations on individual bytes and words. From the CPU's point of view, even much of this manipulation consists of operating on integers that happen to represent addresses instead of data. So when a C program writes a 0 to the 19th entry in a sequence of 4-byte integers, somewhere in the implementation of this operation, the CPU will be adding 4 times, or is that a times? We'll be adding 419 to a base address for the sequence to computer. Let me see what that was in the actual notes. 19. Oh my God. Getting there. There we go. We'll be adding 4. Yeah, it's dot. I don't know what that dot means though. Okay. Dot 19 to the base address for the sequence computer with a program. Unlike many higher level languages, C allows the program direct access to address computations via pointer types, which are tricky enough to get their own chapter. Indeed, most of the structured types that C provides for representing more complicated data can best be understood as a thin layer of abstraction on top of pointers. We will see examples of these in later chapters as well. For now, we can concentrate on integer and floating point types and on the operations that can be applied to them. Chapter 7. Okay, so what we're going to do is, let's say, Valgrind section, rest of chapter 4, 5, and complete chapter 6 on Introduction to C Programming. Okay. All right. We are going to be done for today. Thank you for joining in. Thank you for dealing with my crazy eLisp dragging off of that for a minute. We got through some stuff. Very interested to start doing integer stuff tomorrow and see how far we get that. Thanks for tuning in to Keenan Can Do. Everyone have a wonderful day, and we'll talk to you later. Bye-bye.